Right, so in this first question, it's about specific heat capacity, and this is the specific heat capacity assessed practical. So you make sure you know how to write a method for specific heat capacity, and you are aware of how to use this equation where energy is equal to mass times the specific heat capacity times the temperature change. Right, so in this calculation, we're trying to calculate the energy transferred to the surroundings from the water. So it's quite a simple one because it's using the equation that we're given. So all we need to do is multiply the mass, which is 0.5 kilograms, multiplied by the specific heat capacity, which is for water, which is 4,200. Now remember, water has a really high specific heat capacity, which means it takes an awful lot of energy to raise the temperature of it by 1 degrees C, and that's for 1 kilogram of material. It says that the temperature of water decreases by 22, so that is the temperature change. It doesn't have to go up, it can go down as well. So if we multiply those together, we will get 46,200 joules. Right, the next question says, what is the total energy input to the kettle? Why is the total energy input to the kettle higher than the energy used to heat the water? So the reason is energy is used to heat the kettle up. Right, the next question is revolving around rearranging this equation. So I'm going to write E equals m times c times theta again, and we need to rearrange this equation, and we're going to find the temperature of the water. So we're trying to find this, which is the temperature. So we need to divide by m times c on both sides. So m times c, that's going to cancel out, and therefore our equation, I'll just write up here, is that theta, which is our temperature change, is equal to energy divided by mass times specific heat capacity. So let's put that into our equation. We know that the energy is 46,200. 46,200. We're going to divide that by the mass, which is 0.5. And we're going to multiply that by the temperature, by the specific heat capacity, which is 4,200. Okay, so if we put that into our calculator, now remember when you do this, put this in brackets so you don't get an error. That is going to equal 22. Now 22 degrees C is not the answer because the initial temperature of the water is 100 degrees C. So if the initial temperature is 100 degrees C and we subtract the temperature change, which is 22, then we get our answer, which is the temperature after 2 hours, and that's going to be 78 degrees C. Okay, it asks us now to calculate the average power output from the water in the kettle. So remember, power is equal to energy divided by time. Power is also equal to voltage times current, and it's also equal to current squared times resistance. But for this particular question, we don't need to know that, but just be aware of those for the Unit 1 exam. So the energy is from this part in the question, so that's 46,200. And we're going to divide that by the time taken, and the time taken is 2 hours, so that is going to be 2 times 60 times 60, and that's going to equal 7,200. So if we divide those together, our answer is 6.4 watts. Remember, power is measured in watts. Okay, so this is another question, and this time we're calculating the specific heat capacity, so we need to rearrange it again. So energy is equal to mass times the specific heat capacity times the temperature change. So again, we're going to have to divide by the things that we want. Specific heat capacity is the thing we want, so I'm going to circle that, and we're going to divide by the other things, which is mass and temperature change. We do the same on both sides. The mass will cancel and the temperature change will cancel, so if we rearrange that equation, C is equal to this, which is energy divided by mass times temperature change. Okay, so what is our energy? Well, our energy clearly says here 6930 joules. So 6930 divided by our mass, which is 0.33, and we're going to multiply that by the temperature change. So it says the initial temperature of the liquid in the can was 25 degrees. The can chiller decreased the temperature of the liquid to 20. So that's 25 minus 20, which gives us a temperature change of 5. Okay, so we need to multiply that together. Now this calculation I haven't done yet, so I'm just going to do this on my calculator now. So 0.33 multiplied by 5 gives us 1.65. So I'm just going to put that there. So 1.65, and we need to do 6930 divided by that number. 6930 divided by 1.65, and that gives us 4,200. Now remember, this is the specific heat capacity of water. Now, for getting the units of specific heat capacity, all we need to do is we look at our equation. Energy is equal to mass times specific heat capacity times the temperature change. So how do we rearrange this for specific heat capacity? Well, we did that up there, and we said that specific heat capacity, which is C, is equal to the energy divided by the mass times the temperature change. So now let's look at the units for this. Energy is measured in joules, mass is measured in kilograms, and specific heat capacity, temperature change, is measured in degrees C. So our units are joules per kilogram degrees C. So we can work out our units from rearranging the equation. Okay, what is meant by specific heat capacity? Now remember, the word specific means a kilogram. So the specific heat capacity is the energy required to raise the temperature of 1 kilogram of substance or material by 1 degrees C. Okay, so the key points here is if you've got a kilogram of material and you raise its temperature by a degree, that is the specific heat capacity. Right, the next question. It says a metal water quenches a steel rod by heating it to 900 degrees C before placing it in cool water. The mass of the steel is 20 kilograms. The final temperature is 50 degrees C. Calculate the energy transferred by doing this. So we know that energy is equal to mass times the specific heat capacity times the temperature change, which is equal to 20 multiplied by 850, because that's the change in temperature. 900 minus 50 is equal to 850. Let's write that down. 900 minus 50 is equal to 850, and we're going to multiply that by the specific heat capacity of steel. You can see this is much lower than water. That's telling you it requires much less energy to heat it up or cool it down. So water has a very high specific heat capacity, and metals like steel have a very low specific heat capacity. So that's 420. If we multiply those together, we will get 7.14 times 10 to the 6. So I put this in standard form because it's quite a large number and it's asked for the number in joules. So we can't convert it into kilojoules or megajoules because it's already asked for it in joules. Okay, the temperature of the steel rod eventually returns to room temperature. Compare the movement and energies of the particles in the steel rod and in the air at room temperature. So in the steel rod, the particles vibrate around a fixed point. This is because they are in a solid, and they are arranged in a lattice. And you might want to also talk about the idea that there are free electrons. Air is obviously a gas, and therefore the particles are free to move I'm just going to add a couple of points here. In a gas, they are random, and they have a high kinetic energy, and in a steel rod They are in a fixed position and they have a low kinetic energy. Now remember, in a solid, it's not specifically asking for this, but you need to remember they have much stronger bonds between the particles. So if this is a solid, the particles are held together in a lattice, remember, by stronger bonds. In a gas, there are no or very weak bonds between the molecules or particles, and therefore they are free to move with much higher energy. Okay, so this is the mark scheme for the questions in case you just skip straight to it.